practical program for approaching equations coupled through step MS. Step 1 already we have seen. Once again for recall, find the eigenvalues and eigenvectors of M. Second one, decompose X into its eigenvector components. Step 3, stage scale eigen each eigenvalue component. Step 4, solve for C and transform back to original coordinates. X bar equal to C1 E1 plus C2 E2 plus up to CNN. So final result E vector C vector. So putting all together, so E inverse M equal to, so where step 1, this one step 1, these are step 1, here row, here diagonal matrix, that is eigen of M, here that is MATLAB A, comma E equal to eigen M vector. Putting all together, mx m vector x vector equal to E vector A E inverse x vector. Step 2, these steps, step 2, transform into eigen coordinates. Step 3, this is a scale by lambda I along the ith eigen coordinate. Sorry, this is not a lambda, scale by lambda I along the ith eigen coordinate. This E, fourth step, transform back to original coordinate system. Left eigen vectors, left. So E inverse equal to, in this column, E vector left, E1 left, that is E vector 1 left, E vector 2 left, up to E n left, E vector n left. The rows of E inverse, these all are these rows, first row, second row, third row, in the same column. So the rows of E inverse are called the left eigenvectors. The rows of E inverse are called left eigenvectors because they satisfy E inverse M equal to lambda of E inverse, because satisfy E inverse M equal to lambda E inverse. Together with the eigenvalues, they determine how X is decomposed into each of its eigenvector components. Together with the eigenvalues, they determine how X decompose into each of eigenvector components, into each of decompose. Okay. Putting all together, continuous M original matrix reform, back to original form, E lambda E inverse. E vector lambda vector E inverse. Matrix in eigen coordinate system. Matrix in eigen coordinate system where lambda equal to lambda 1, lambda 2, lambda n diagonal matrix. Okay. Trace and determinant. Trace and determinant. Original matrix E lambda E inverse. All are vector form. Matrix in coordinate system is lambda. Matrix in eigen coordinate system. Note M and lambda look very different. This one M, this lambda, what look very different means how it is. Or there are any properties that are preserved between them? Yes, two very important ones. What? Sum of diagonal entries. Lambda 1, lambda 2 up to lambda n. I equal to summation of I equal to 1 to n lambda I. TR of m equal to TR of lambda. This is the same sum of diagonal. Determinant of matrix equal to determinant of lambda equal to lambda 1, lambda 2 into up to lambda n. I equal to 1 to n lambda I. Special matrix. Special matrix, normal matrix. Normal matrix. The special matrix under here normal matrix. All eigenvectors are orthogonal. In the normal matrix, all eigenvectors are orthogonal. Orthogonal. Can transform two eigen coordinates change per basis with a simple rotation of the coordinate axis. Here, like this picture showing. A normal matrix eigenvector matrix E is a generalized rotation unitary orthonormal matrix defined by E inverse equal to E transfer. Here, this is the picture. Transform eigen coordinates change basis with a simple rotation of the coordinate axis. Normal matrix eigenvector matrix E is a generalized rotation unitary or orthonormal matrix defined by E inverse equal to E transfer. All eigenvectors are orthogonal. This is the very important point for normal matrix. Can transform to eigen coordinates change basis with a simple rotation of the coordinate axis. E is a rotation unitary orthogonal matrix defined by E inverse equal to E transfer. Okay, where if E vector equal to this the what one column up to n rows, one column. Here then E after E transfer, what will come? E inverse equal to E transfer. This is same, no? E11, E21 up to En1 coming, no? In the first row, up to n columns. So both are same, no? E is rotation, unitary or orthogonal matrix defined by can transform eigencoordinates change basis with a single rotation of the coordinate axis. All eigenvectors are orthogonal. That's why I tell you. Special matrix, same normal matrix. Eigenvector decomposition in this case. Eigenvector decomposition in this case. M equal to E lambda E inverse equal to E lambda E transfer. Both are same. Already we have seen in the last slide. So here this is the first column in the this row. E power 1, E power 2 up to E power n. This row. Lambda into E transpose. This one here coming. So E power 1. This takes pura this row totally sorry. This column coming to here as row. Okay. Left and right eigenvectors are identical. Left and right eigenvectors are identical. Left and right eigenvectors are identical. Same no? Here this one here, same coming here. Okay. Then sorry. Coming here. Okay. Sorry. Okay. Special matrix. In this special matrix, symmetric matrix. In the symmetric matrix, S transfer equal to S. Covariance matrix, Pope-filled network. That is example. Properties. Eigenvalues are real. Eigenvectors are orthogonal. It is normal matrix. It is a normal matrix. Normal matrix. Symmetric matrix. ST equal to S. Okay. Okay. SVD. SVD decomposes matrix into outer products. Example, a neural, spatial mode and temporal mode. N into D, N cross T. T equal to 1, T equal to 2, T equal to up to N, T, caps T. Here N equal to 1, that is row, N equal to 2 up to N equal to N. That is column